In the quiet hum of a university laboratory, a revolution began not with a bang, but with two letters, LO. The date was October 29, 1969. Inside a lab at UCLA, Professor Leonard Kleinrock and his student Charlie Klein were about to send the first message over a brand new computer network called the ARPANET. Their target was a computer 350 miles away at the Stanford Research Institute. The plan was simple. Klein would type login to remotely access the Stanford machine. He and his counterpart at Stanford, Bill Duvall, were on an open telephone line, an analog backup for a digital dawn. Klein typed the L. Over the phone, he asked, "Did you get the L?" Duvall replied, "Got the L." Klein typed the O. "Got the O" came the confirmation. Then, Klein typed the G, and the system crashed. The immense potential of the network had, for a moment, overwhelmed its own humble beginnings. The first message ever sent across what would become the Internet was, fittingly, LO, as in, lo and behold. An hour later, they succeeded, but that initial fragmented message had already made history. But why was this network being built in the first place? To understand the ambition behind the ARPANET, you have to feel the chill of the Cold War. After the Soviet Union launched Sputnik 1 in 1957, the US government created the Advanced Research Projects Agency, or ARPA, with a mandate to prevent future technological surprises. A key fear was that a single nuclear strike could decapitate the nation's centralized command and control communications. This led a brilliant engineer at the RAND Corporation named Paul Baran to design a communication system that could survive a nuclear war. In the early 1960s, Baran envisioned a distributed network with no central core. It would be a redundant, web-like structure. If one path was destroyed, messages could be automatically rerouted. To do this, he conceived of a method he called message blocks, chopping data into small, addressed packets that could be sent across the network and reassembled at their destination. This concept, later known as packet switching, was the key. Independently, in the UK, a scientist named Donald Davies was developing the exact same idea for more efficient civilian computer communication. He even coined the term packet. While the specter of nuclear war provided the funding and urgency, a more immediate, practical motivation came from an ARPA director named Bob Taylor. In his Pentagon office, Taylor had 3 separate teletype terminals, each connected to a different, incredibly expensive ARPA-funded supercomputer. To use the computer at MIT, he had to physically move to a different terminal than the one for UC Berkeley. He thought it was ridiculous and envisioned a single terminal that could connect to any computer on a unified network. This would allow researchers to share not just data, but precious computing power. It was this dual vision, a resilient military network and a collaborative scientific tool, that gave birth to the ARPANET. A project this grand was the work of a community of visionaries. The philosophical seeds were sown by a psychologist and computer scientist named J.C.R. Licklider. In the early 60s, Licklider, as head of ARPA's computing office, wrote memos about an intergalactic computer network, imagining a world where everyone could access information and programs from anywhere. He saw computers not just as calculators, but as interactive communication devices. He was the prophet. The builders were Bob Taylor, who secured a $1 million budget, and Larry Roberts, a young scientist from MIT, whom Taylor recruited to be the chief architect. At a pivotal meeting in 1967, another researcher suggested a crucial innovation. Instead of connecting all the host computers directly, they should use smaller, separate computers at each site just to handle the network traffic. Roberts adopted this idea. These machines would become the Interface Message Processors, or IMPs, the world's first routers. Roberts synthesized the work on packet switching from both Baran and Davies, creating the blueprint for the network. And providing the mathematical proof that it would all work was Leonard Kleinrock at UCLA. His work on queuing theory was so fundamental that his lab was chosen to be the very first node on the network. All of these theories needed a physical form. The critical piece of hardware that made the ARPANET possible was the IMP. The contract to build these machines was won not by a giant like IBM, but by a small Cambridge firm called Bolt, Beranek and Newman, or BBN. The IMP guys at BBN, led by Frank Hart, had less than a year to build the first one. They based it on a ruggedized Honeywell minicomputer, encased it in a massive steel frame, and gave it a mere 12 kilobytes of memory. The BBN team wrote the complex software that performed the packet switching, taking data from the host computer, breaking it into packets, and forwarding them to the next IMP on the line. In August 1969, a 1-ton IMP was delivered to Kleinrock's lab at UCLA. A month later, IMP number 2 arrived at Stanford. Then came UC Santa Barbara and the University of Utah. The stage was set. After that first halting low message, the 4-node network became fully operational by December 1969. The software that allowed the host computers to talk to each other was called the Network Control Program, or NCP. With a stable network, the focus shifted to what it could do. The first applications were foundational: Telnet, which allowed a researcher to remotely log into another computer, and FTP, the file transfer protocol for moving files. But the network's true killer app was a complete surprise. In 1971, a BBN engineer named Ray Tomlinson was working on a messaging program for users on the same computer. On a whim, he modified it to send a message file to a user on a different computer over the ARPANET. He needed a way to separate the user's name from the computer's name. Looking at his keyboard, he chose the @ symbol. He sent the first network email to himself between 2 computers sitting side by side. He told a colleague, "Don't tell anyone, this isn't what we're supposed to be working on." But it spread like wildfire. Within 2 years, a study showed that 75% of all traffic on the ARPANET was email. Email transformed the network from a tool for remote computing into a medium for human connection, creating the first online communities. The ARPANET was a success, but it had a limitation. Its protocol, NCP, was designed for a single network, but the future was a network of networks, an internetwork. ARPA was already funding satellite and radio networks, and NCP couldn't connect them. A new, universal language was needed. The challenge fell to 2 engineers, Robert Kahn of ARPA and Vinton Cerf of Stanford. Their solution, designed in 1973, was to split the process into 2 layers. The first was the Internet Protocol, or IP. Its only job was to get packets from one place to another using an IP address, like a mailing address on an envelope. The second layer was the Transmission Control Protocol, or TCP. Running on the host computers, TCP's job was to ensure reliability, breaking data into numbered packets, and on the receiving end, reassembling them in order and requesting retransmissions of any that got lost. This design was ingenious. It moved the intelligence to the edges of the network and kept the core of the network simple and adaptable. On January 1, 1983, a day known as Flag Day, the old NCP protocol was turned off. Every machine on the ARPANET had to switch to TCP/IP. The modern Internet was born. The adoption of TCP/IP marked the passing of the torch. In 1983, the network was split. The military components became MILNET, while ARPANET remained for research. But a new player was emerging, the National Science Foundation, or NSF. In 1985, the NSF launched its own network, NSFNET, to connect 5 new supercomputing centers. Crucially, they adopted TCP/IP as their standard. The NSFNET quickly grew, creating a high-speed backbone that eclipsed the aging ARPANET. In 1990, the ARPANET, its mission accomplished, was officially decommissioned. For most users, the NSFNET was the Internet. The final step was privatization. The NSF had a strict policy against commercial traffic, but as the network's value became obvious, the pressure mounted. In 1991, the restriction was lifted. By 1995, With a thriving ecosystem of commercial internet providers building their own backbones, the NSF dismantled its network. The government had successfully nurtured the internet from a military experiment into a self-sustaining global enterprise. From a single 15-foot cable in a lab to a global network coursing through our lives, the journey is extraordinary. The world we live in is a direct descendant of that failed login attempt. The accidental message, "Lo," has echoed through the decades. Lo and behold. The legacy of the ARPANET is not just its technology, but its core principles: decentralization, open protocols, and a culture of collaboration. Its pioneers didn't foresee social media or streaming video. They wanted to share computer time, but by creating a tool for machines to talk to each other, they inadvertently built the most powerful platform for human communication ever invented. Those two humble letters were the quiet beginning of a revolution that is still unfolding.